Okay, we are continuing on our lesson about alkenes, and we've so far seen 4 reactions that add a variety of things to alkenes. The first reaction was the hydrohalogenation reaction, where we add an H and a halogen to the alkene. And so we went through that. Reaction 2 was called the dihalogenation reaction. Actually, there was a typo here. It's not called the dihydrohalogenation. You're not going crazy. It's just called the dihalogenation. That was a mistake in my notes. I apologize. Let me fix that. And this reaction put 2 halogens on the alkene. So we use Br2 and we can add 2 bromines. And if you use Cl2, you'll add 2 chlorines. We looked at the bromonium intermediate, which was a kind of unique mechanism that went through a 3-membered ring with the bromine. And then we saw that just by changing the solvent from CCl4 to water, we then created halohydrins, where we added OH and Br across the alkene. And we also changed the solvent to an alcohol, and then we added OR and a halogen to the alkene. Now we're looking at reaction 5, and it turns out that reactions 5 through 7 all do the same thing. They all add H and OH. So reactions 5 through 7 are ways to add H and OH to an alkene. 3 different ways to do the same thing. And if you think about it, that's the same thing as adding water, because what is H and OH? That's H2O, which is the elements of water. So reactions 5 through 7 are all considered so-called hydration reactions, and that they add water. Okay, let's take a look at reaction 5. I'm going to do the full screen here. So reaction 5 is called acid-catalyzed hydration. Okay, and let's take a look at what this reaction is. It takes an alkene, and if you treat it with H2SO4, which is sulfuric acid, and water, so before we've seen sulfuric acid in heat, now we're seeing sulfuric acid in water, that is going to get rid of the double bond, and on one of the carbons you're going to have an OH group, and on the other you're going to have an H. So it's a way of adding H and OH to the double bond. In terms of the stereochemistry, there's no control. As we'll see in a moment, the mechanism goes via a carbocation, and you know that carbocations, they don't have any stereo control because they can attack either the top or the bottom. And in terms of regiochemistry, this is going to be Markovnikov. And if you remember what that means, it means that the H is going to go on the carbon with the most number of H's. By the way, this reaction sucks in practice. So generally, you will use reactions 6 or 7, which we'll see in a moment, which do a better job of this reaction. But I won't take off points for using this reaction. It's a totally fine reaction, just in reality, it doesn't work very well. I've actually tried it myself, and it's not great. A lot of side reactions with H2SO4. Let's take a look at the mechanism. And for the mechanism, I'll show it with an alkene that has 2 carbons on the right and 2 hydrogens on the left. And in the first step, the alkene is actually going to react with hydronium. So that's H3O plus. Now, where is H3O plus coming from? H3O plus is formed when H2SO4 and H2O react with one another. So the H2SO4 is getting protonated by the sulfuric acid, and it's forming some H3O plus, which is called hydronium. You may remember that from general chemistry. And so what happens is the alkene grabs a proton from H3O plus. And what happens next is that a carbocation forms. So in this case, the proton gets added to the side of the alkene that has the most protons already, which is the left side. This is Markovnikov's rule. So we're adding that new H to the left, and we're getting the carbocation on the right. Because as we're destroying that double bond, one side of the double bond gets to keep its octet because it gets to bond with hydrogen. The other side of the alkene gets nothing. So it's left with the carbocation. And of course, we'd like to form the carbocation on the more substituted side where it's more stable. Then water acts as a nucleophile and attacks the carbocation. Okay. So now we're almost to the product. We just have a pesky proton on our water still. The oxygen has a positive charge. We still have that hydrogen on the left. And now another molecule of water, or you can use a generic base, your choice. I'll just show another molecule of water coming along. Takes the proton, and we're left with an alcohol. Okay. And there's our final product. It's the alcohol, where the OH group gets added to the more substituted side of the alkene, and the H goes on the less substituted side of the alkene. And notice what happens to this water molecule when it takes up a proton. It creates H3O plus again. And that's why they call this acid catalyzed, because notice that the H3O plus is regenerated by the reaction. And when you have a substance that's regenerated in a reaction, we call that a catalyst. So this is the H3O plus regenerated. By the way, if I ask you to draw the mechanism of this on the exam, you don't have to show the H3O plus being regenerated. You just have to draw the major organic compound. So don't worry about this. I was just showing it to you so that you can see why they call it acid catalyzed hydration and not just acid hydration, for example. Okay, so that's reaction 5. What's reaction 6? Good news about reaction 6, no mechanism that you need to memorize for this class. The mechanism is very complex. So reaction 6 is coming up next. In reaction 6, we're going to call this the oxymercuration reduction. As the name implies, it's a two-step process. And it essentially does the exact same thing as reaction 5. It just does it way better. The only downside to reaction 6 is it uses toxic mercury, which is, of course, highly poisonous compounds with mercury. So if we take this alkene and we treat it in step 1, the reagents are mercury acetate. So mercury is Hg, and it's OAC2, the 2 acetates on that mercury, and water. And then in step 2, we could do a reduction reaction, which is NaBH4, sodium borohydride, we've seen that before, NaOH, and H2O. And those are the conditions. The product of the reaction is an alcohol. We add OH to the more substituted side of the alkene, just like in reaction 5, and we also add an extra H that I'll draw in, but you wouldn't even have to draw in that H because remember, implicit hydrogens can be left out, and that H goes on the right carbon, the less substituted carbon. Stereochemistry, there's no stereochemistry for this reaction. It's random. So you don't have to worry about wedges or dashes. And the regiochemistry is Markovnikov. And that's because the rich get richer. The hydrogen goes on the less substituted carbon. Okay? So that is the oxymercuration reduction reaction. And don't worry about the mechanism. No mechanism. It's very complicated. I can show you if you want, but it's honestly, it's a freaking nightmare. Google it if you want. You'll see why I don't make you know it. It's too hard. It's hard for me even to remember. There's so many steps. Okay, let's take a look at reaction 7. Reaction 7 is actually my favorite of all the alkene reactions personally because I love boron. It's my favorite element. I did a lot of research with boron in my PhD, and it's just a fascinating element, and there's a great reaction here in reaction 7. This one is called the hydroboration oxidation. And because this is my favorite reaction, I always put at least one of these on the final. The hydroboration oxidation works as follows. Again, we'll draw that same alkene. And the conditions for the hydroboration oxidation, it's another two-step process. It's very important that you write step 1 and step 2 and not just write everything together. It's specifically step 1 and step 2. Step 1, we're going to add a substance called borane. So borane is BH3. And a borane is a gas, and it's not very convenient to handle because, I mean, you got to measure out a gas. You can imagine that's not easy, especially if you want to measure out a certain amount. So what they typically do is they use something called BH3THF. It is a complex of boron and THF that makes it a liquid. So the THF is just sort of a spectator, kind of like a hitchhiker that's there, but the borane bonds to the THF loosely and creates a liquid form, which is more easy to measure. Okay, but the THF is kind of like a solvent, but it's kind of more than that. It holds everything together. Okay, and then step 2 is going to be hydrogen peroxide, which is H2O2, NaOH, and H2O. Okay, remember those conditions. Step 2, it's like everything kind of can like swirl together in your brain. So just remember it's hydrogen peroxide, sodium hydroxide, and water. The product of the reaction is actually the anti-Markovnikov or non-Markovnikov product, where the alcohol gets added to the less substituted side. It's also interesting to note that the alcohol and the hydrogen, they both get added syn. So I think it's the only reaction we'll see in this chapter where the two groups that we add to the alkene go on the same side. So this is stereochemistry plus an enantiomer, of course. We don't know, we just have control of the relative stereochemistry. So we can't say whether they're both wedge or both dash. All we can say is that the H and the OH are both of the same direction. And so we call this syn addition as opposed to anti-addition. And the regiochemistry is actually opposite of all the other reactions. It's non-Markovnikov. And that is that the hydrogen goes to the more substituted carbon. This is opposite of what we would expect for these sort of reactions. So really reactions 6 and 7 are kind of complementary to each other. If you want to turn an alkene into an alcohol, you can do that by adding the alcohol to the more substituted side of the alkene using reaction 6. And if you want to turn an alkene to an alcohol by putting the alcohol on the less substituted side, use reaction 7. So those two are really powerful reactions to have in your toolkit, especially when you consider how many different reactions you can do with alcohols. Once you turn an alkene into an alcohol, then you can do all sorts of the alcohol reactions on it. You can do the PCC, you could do the Jones, you could turn the alcohol into a halogen and do SN2. So reactions 6 and 7 are like so important because they are the bridge between alkenes and the alcohols chapter. And we know the alcohols chapter was huge, really important chapter. Now, I'll make you know the mechanism for step 1 only. Don't worry about the mechanism for step 2. The mechanism for step 1 is as follows, and hopefully this will help you explain why it's non-Markovnikov. What happens is the alkene and the boron line up with each other, kind of like they're doing, you know, have you seen those birds on those nature shows that do a mating ritual? You know, one bird will kind of walk along and then another bird will kind of walk alongside it, and they're doing like a mating ritual, and they're trying to impress the other bird. I kind of think of this as a mating ritual as well. So one bird is our alkene, and the other bird is the borane. And the borane is going to line up so that one of its boron-hydrogen bonds lines up perfectly with the alkene. See how they're parallel? It's important when you draw the mechanism that you show these bonds parallel to each other. Okay, then what happens is they decide to do their mating. Okay, that's fun. So the alkene grabs the boron, and the boron-hydrogen bond grabs the alkene, just like that little square dance, if you will. And notice the boron, which is a little bit bigger than the hydrogen, likes to orient itself over the less substituted carbon, whereas the hydrogen, which is small, is willing to be next to the bigger methyl group. So that's why they line up this way, and this is actually the reason for the non-Markovnikov selectivity. It's because the slightly bigger boron likes to be near the least substituted side. The boron would not like to orient the other direction, because then the big boron would be near the big methyl group, and that would be bad. So it's sterically driven. Okay, then what happens? And because this is this mating ritual where everything's happening at the same time, that also explains why the boron and the hydrogen get added to the same side. So on the right side we have BH2, since one of the hydrogens is gone now, and the other hydrogen is on the other carbon, and we still have that methyl group now, which I'll have to draw that as a dash because the hydrogen is coming in as a wedge with the boron, so the methyl group has to be a dash. It has no other place to go. This is called an organoborane. And this was my PhD. I did a lot of PhD research on these organoborane compounds, very useful compounds. They're kind of like chemical wildcards. There's a reaction that can turn the BH2 group into pretty much anything. There's a reaction that turns it into an iodide. There's a reaction that turns it into an alcohol. There's a reaction that turns it into an aldehyde. There's a reaction that turns it into a bromine, chlorine, cyanide. So these are kind of like chemical wildcards. In this case, we're doing the reaction that turns it into an alcohol. That's the H2O2, NaOH, H2O. And don't worry about the mechanism. It's a cool mechanism, but it's too complicated for you to worry about. So the net result is going to be replacing the boron with oxygen, and it does so with retention of stereochemistry. So the boron, which was wedged, stays wedged as it goes into the alcohol, and the hydrogen, of course, stays there. And then we get our final product. So organoborane, this thing here, don't worry about the mechanism. Okay. So now we are up to reaction number 8. Reaction number 8 is called the epoxidation reaction, and it's a very powerful reaction also that comes up again and again. And the epoxidation reaction is very simple. You take an alkene and you treat it with a reagent called MCPBA, which is obviously an acronym. It stands for metachloroperoxybenzoic acid. I'll show you the structure in a second. The solvent is typically dichloromethane, so CH2Cl2, just like PCC and stuff. And the product, it actually turns the alkene into an epoxide. And we've seen there's a lot of reactions that involve the epoxide, so you can imagine you can create some pretty awesome test questions, taking an alkene, turning it into an epoxide, and then doing one of the epoxide reactions with it. I told you I'd tell you what the MCPBA is. You don't need to know this, but I'll just show you for fun. It stands for metachloroperoxy benzoic acid. And the structure looks like this. It's a benzene ring. There's a chlorine on it, and then a peroxy acid. So the key is this oxygen-oxygen bond is quite electrophilic. So this is a weak oxygen-oxygen bond, and it's electrophilic. Okay, take a look at the mechanism for this. I've never seen a crazier mechanism in my life. This has got to be the craziest mechanism. In fact, I'm skeptical that this is even true. How do they even know this? Okay, so the mechanism's looking something like this. You have the alkene, and similar to the borane with the mating ritual, the metachloroperoxybenzoic acid will line up. Oops, sorry, my screen's going a little crazy. The MCPBA is going to line up with the alkene and look kind of like this. So I'm kind of running out of room. Let me just scoot it down a little bit. I'm going to just abbreviate the benzene ring there as AR, just so I don't have to draw the whole thing out. And you can do that also. Okay, so all the action happens actually at the second oxygen, so the oxygen that's far away from the CO double bond. Okay, watch these arrows. Tell me if this is enough arrows for you. The alkene attacks the oxygen. The oxygen attacks the alkene. Okay, that's not too crazy. The weak oxygen-oxygen bond breaks towards the CO double bond. The CO double bond grabs the hydrogen. And then the hydrogen-oxygen bond breaks. Seriously? Is that even reasonable? That is so many electrons moving at once. I mean, I just laugh looking at that every time. I guess I have a weird sense of humor. To me, that is just so ridiculous. But yes, you need to memorize that. I'm serious. And then in one step, that's the key here, so the whole thing happens at once. You're left with a byproduct of chlorobenzoic acid. You don't need to write that. This is just the byproduct. So when the reaction's done, there's a lot of this carboxylic acid left over. Plus, you get the beautiful epoxide out. Okay. So that is the mechanism. And yes, you need to memorize these arrows. It's definitely fair game for me to ask that. The regiochemistry, what do you think? Not applicable. We're adding the same thing to both sides of the alkene, so it doesn't matter which side gets what, because both sides are getting the same thing. Stereochemistry is also syn. I lied when I said the hydroboration was the only one. This one has to be syn because you can't have a trans epoxide. Let me show you what I mean. So if I have this alkene and we treat it with MCPBA, don't worry about the solvent, we get this. We never get this because this is impossible. You can never have a trans epoxide. Imagine trying to make a triangle where you've got one bond going up and the other going down. Where the heck's the oxygen supposed to go? It's got nowhere to be. So that's why it always goes on the same side for an epoxide to make a triangle. So there's no such thing as a trans epoxide. Okay, just two more reactions left. And we're done with the alkenes. Okay, reaction 9 is called catalytic hydrogenation. Actually, I lied. There's 11 reactions. Yeah, there are 11. So we've got 3 more left. But it's okay. This one's an easy one. Catalytic hydrogenation is also called reduction, catalytic reduction. And this is just a way to delete alkenes. So if you have a CC double bond, and the reagents for this are hydrogen gas, and then there's a metal catalyst, palladium on carbon. It's basically charcoal sprinkled with some palladium metal. And the solvent is typically methanol or ethanol. Solvent's not important here. And it's going to add hydrogens to both sides of the alkene. In effect, this deletes the alkene, right? Because you don't have to draw in those hydrogens. So it takes an alkene and turns it into an alkane. No mechanism. Don't worry about the mechanism. The regiochemistry, well, we're adding the same thing to both sides, so none. Stereochemistry, it's syn addition. God, I really lied. There's a lot of syn addition ones. Okay, syn addition. So let's take a look here. If I took this alkene and I treat it with H2, palladium on carbon, and why don't I do ethanol as a solvent? That's also acceptable. It's going to add 2 hydrogens to the alkene, and it's going to add them from the same direction. So we'll get wedged hydrogen, and then the 2 methyl groups will be forced to become dashes. Take a look at another reaction. How about if we had this guy? And treat that with H2, palladium on carbon. The product is that. So the reaction deletes alkenes. Okay. And notice the benzene ring is not affected by the reaction. The aromatic ring is unaffected. If you remember, I actually showed this reaction before, way back when we were learning about the aromatic rings, and we talked about how there were the aromatic stabilization energy and how they use the hydrogenation reaction, the heat of hydrogenation, to actually discover the aromaticity properties. And so it turns out that this reaction will remove the alkenes of the double bond inside the benzene, excuse me, but it requires extremely high pressure. So unless the pressure is greater than 90 bar, which is equal to 1,305 psi, which is an extremely high pressure. Compare that to the tire pressure of your car, which is about 40 psi. So, you know, your tires on your car are pretty pressurized. You know, if a tire explodes, that's a lot of pressure. You know, that can definitely hurt somebody if your tire explodes. So imagine that's just 40 psi. But in order to get rid of the double bonds in the benzene ring, you need 1,305 psi. You need very specialized high pressure equipment to do that. I've never done that in my career, so that's kind of beyond me. I don't know. They use something called a bomb. That's what I know. It looks. I'll show you a picture of it in the lecture of what a bomb looks like. But it basically looks like a little metal cylinder, and it can hold extremely high pressure. Okay, so that's reaction 9. Let's take a look at reaction 10. Reaction 10 is called the dihydroxylation reaction. Have you ever wanted to turn an alkene into 2 alcohols? Well, now you can with the reaction 10, available now for a limited time only. Actually, no, it's been available since the beginning of time because it's an organic chemistry reaction. It was actually discovered not too long ago, though. And the way the reaction works is it starts with an alkene, as always, and the reagent is very unusual. It's osmium tetroxide, so OSO4, and step 2 is H2S, which is required. It's a reducing agent that's needed for this reaction to work. It turns out the person who discovered this reaction made a great sacrifice to chemistry. It turns out that osmium is highly toxic to the optic nerve, and so it causes blindness. It also has a terrible property in that it is quite a volatile solid. So as you're weighing this out on the scale, osmium vapors are rising and getting into your nose and eyes, causing blindness. The person who discovered this reaction permanently lost their eyesight due to that osmium tetroxide. So, like I said, a great sacrifice to chemistry. We need to be very, very careful with osmium as it is highly toxic. And of course, we really, really value our eyesight. As humans, we rely so heavily on that. So there have been more modern methods that get rid of the osmium, but this is the traditional way to do it. So we'll leave the osmium for this. The product of the reaction is a syn diol. So it turns the alkene into 2 OH groups, and it's a cis or syn addition of a vicinal diol. Remember that term vicinal, meaning that's 2 OH groups next to each other. Vicinal means on adjacent carbons. So OH on adjacent carbons. I think I mentioned this in the second NMR lesson. We talked about the word vicinal. And you could also call this a 1,2 diol, since it's 2 OH groups, 2 alcohols on the 1 and the 2 carbon. Pretty useful reaction. Imagine doing PCC on that product. Nice. Stereochemistry. Syn addition. So it adds the 2 OH groups from the same side. It's so funny. I said at the beginning, I think this is the only syn reaction. I must have been thinking, and I must have had it backwards. Literally every reaction today has been syn addition. Okay. And the regiochemistry, not applicable because we're adding OH to both carbons, so it doesn't matter who gets what. Let me ask you a question here. How would you make a trans diol? How would you make a trans diol? Answer, pause it if you don't want the spoiler. Go via epoxide. So if you wanted 1 wedge, 1 dash, you could do it like this. Take your alkene, treat it with MCPBA, and you would get the epoxide Of course, the epoxide has to be both wedge or both dash. You can't have a trans epoxide. And then open the epoxide with NaOH. That's going to do SN2 on one side of the epoxide. Doesn't matter which side because we're still adding OH. And then that would lead to the trans diol because we have inversion at the site of attack. And then if you want the cis diol, you can just do the step 1, OSO4, step 2, H2S. Don't forget that H2S, it is needed. And then you'll get the OHs on the same side. So I usually do like to put a question like that on the final just to see if you remember how to make both the trans and the cis diol. All right, last reaction. I promise this is the most fun. Think of this like a treat that I'm giving you. It's reaction 11. And the final alkene reaction you need to know. This one's called ozonolysis. And it is the only reaction that's involving ozone. Here's how the reaction works. Take an alkene and treat it in step 1 with ozone, which is the chemical formula O3. You probably wonder, where do you get ozone? You have to buy a machine called an ozonator that makes ozone on demand. It's an ozone generator. You pump oxygen into it, it applies electric current, and it converts some of that oxygen into ozone, which is then used in the reaction. By the way, a lot of students think ozone's good. Ozone's very bad. Ozone is highly toxic, it's highly corrosive, very nasty stuff. The reason we think ozone is good is because the ozone layer protects us from the sun. That is true. However, it's good that it's way up there in the upper atmosphere, in the upper stratosphere, where it can do its job blocking from the sun. Down here on our level, you do not want to be breathing in ozone. It will kill you very quickly, very toxic. So ozone needs to stay up there in the sky, not down here in Los Angeles. Unfortunately, ozone is a component of smog. So we do have some ozone here in Los Angeles from all the cars that are driving around. You also need step 2, which is DMS, another reducing agent like H2S. And don't worry about the mechanism on this one. And what this is going to do is basically act like a pair of molecular scissors. It's going to cut the alkene right down the middle. So imagine taking a pair of scissors and snipping the alkene. You're actually going to get 2 products out. It cuts the alkene right down the middle and makes ketones and aldehydes. Isn't that cool? So you can split. It's the only reaction we've actually learned that lets us break a carbon-carbon bond. And not just a carbon-carbon bond, but a carbon-carbon double bond. So we're cutting it right down the middle, and we're getting 2 ketones, or a ketone and aldehyde, depending on if there's hydrogens or carbons on both sides. So the net result is we break alkene down the middle, and products are ketones and aldehydes. Of course, whether it's a ketone or aldehyde depends on the alkene. All right, let's take a look at another example here of the ozonolysis reaction in work. Okay, here's a lovely alkene. The ozone is going to be added in step 1. Step 2, DMS, dimethyl sulfide. We're going to apply our molecular scissors. You don't ever have to draw the scissors. I just like drawing them. It's going to cut that alkene. It only targets the alkene. And so then we're going to get that ketone. And then what's the other product? It's going to look like that. We'll just move it aside here. And that is actually an aldehyde because there's a hydrogen here, right? There was a hydrogen on this carbon that was not drawn in, but it was there. And so that's why when we do the ozonolysis reaction, we get a ketone and an aldehyde. All right, let's do one more just for fun. What if we had an alkene in a ring? No problem. Same thing is going to happen. Let's get our molecular scissors going. Okay, there they are. And now this is interesting because we're going to cut the alkene, but it's still connected along the left-hand side. So to draw the product, what I recommend you actually do is just kind of redraw the starting material, but make the alkene really long, kind of like that. And then what I do is I just erase right down the middle of the alkene and make CO double bonds there. See that? So that's what the ozonolysis reaction does. And then now we can kind of draw this out a little bit nicer. And so we can see it's got aldehyde up here and aldehyde down here. That looks a little bit nicer. Or you could even kind of stretch it out and make it straight. So I can just count the carbons to make sure I have the right number. 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So that would be the same thing. You can either draw it, you know, still bent up in the ring shape, or you can stretch it out and make it straight if you want. I mean, if you can do it, I like this, but I'll still give you full credit for that. And just to show you here, DMS is the following. It's dimethyl sulfide. So it's sulfur with 2 methyl groups on it. Smells like broccoli. In fact, it's what's responsible for the kind of sharp smell of broccoli, dimethyl sulfide. But in this case, it's used as a reducing agent in the ozonolysis reaction. Okay, so we definitely need a lot of practice with all these reactions. I'm just showing them to you now, and then the real fun is going to be actually using all these reactions. I've given you an incredible toolbox right now. You can do so many things to molecules now. The complexity has just tripled in this class because now all of the alkenes can be used in synthesis. You can turn alkenes into halogens. You can turn alkenes into alcohols. You can turn alkenes into, now with the ozonolysis reaction, aldehydes and ketones. So there's a lot for us to explore. So take a look at these reactions. Make sure you understand these reactions, what they do. And in our live lesson, we will go through some problems involving these reactions, and we'll see if we can keep it all straight. All right. See you later for now. Bye-bye.